Today I'm going to share the results of my project generating human-like mouse cursor trajectories from featural task data using CAVE GRU. So my research field is ACI. Our lab member already know that, so let's skip it. So the you all know that many ACI studies require large amounts of mouse movement data. At first, collecting data sounds simple, but recruit participants and ask them to click target. But in reality, things are not that much simple. So our experiment, each participant had to perform more than 30,000 clicks, which took over 2 hours of continuous interaction. So we need to short this task. As shown in the previous example, collecting mouse trajectory data is not as simple as it seems. So in my previous experiment, each participant had to perform over 20,000 clicks in each session, less more than 2 or 3 hours, including breaks. So this makes repeat validation and repeat prototyping difficult. Therefore, our main research question is, can we generate human-like cursor trajectories under given test condition instead of collecting new user data every time? Before going into the details, this is the short experimentary project. So my goal is not to fully replace human experiment, but to first test how far we can generate cursor trajectories that preserve human movement characteristics. Based on this, I evaluated the feasibility and potential of the proposed model. Our project goal is to generate human-like cursor trajectories from recorded movement data. Specifically, we want to learn how task conditions such as movement distance and target width affect human cursor movement. Then, instead of collecting new user data every time, we aim to generate realistic trajectories computationally. This leads to the base of the featural. So we already know featural what is the featural task is. So we skip it this slide. So before discussing the deep learning model, it is important to understanding the nature of mouse trajectories. The mouse trajectories is not simply an image of the movement fetch. Instead, it is a time series sequence that records how the cursor moves from one target to another. Because the trajectories contain temporal information, the spacing between points implicitly reflect movement speed and direction over time. In addition, movement behavior changes depending on the task condition. For example, target distance and target width influence how people move the cursor. This naturally leads to two requirements. First, the model should handle sequential time series data. Second, it should generate trajectories conditioned on task parameters. So our model is conditional CVAE combining with the GOU. It takes the movement condition, distance A, target width W, difficulty ID, and duration, and generates normalized trajectories. An encoder and decoder, both GRUs, are connecting through the lattice vectors Z, capture the variation in human movement. Every trajectory is normalized, so it starts at 0.0 and ends at 1.0. The trajectory normalized is I explained later. So what is a CAVE? The conditional variational autoencoder is a generative model that learns a latent space and generates new samples conditioned on given information, diverse, controllable, and realistic. The gate recurrent unit, the GRU, is the recurrent network for sequencer data. It captures temporal dependencies through updates and reset gates, and it's lighter than LSTM. So I choose the GRU compared with the LSTM. So it's well suited for variable length sequence. So why we combining CAVE and GRU? Mass trajectories are both condition dependent and highly variable. Multiple human-like trajectories can exist under the same featural conditions. CAVE gives us diversity and control basis on the featural conditions A, W, and ID, and duration. GRU gives us the temporal structure needed to generate these as coherent sequences. Together, they produce human-like causal trajectories. So putting it together, the encoder compresses a real trajectory x and its condition d into the latent vector z. And the decoder reconstructs the trajectory x prime from z and the condition d. Here, the latent vector z captures the specific style of the participant, and the condition d determines the characteristic of the task. Before training, all trajectory need to be normalized, so we normalize it. So since trajectories lengths vary from roughly 20 to 120 points, we resample them to a fixed length of 64 points. And we also normalize the coordinates so that every trajectory starts at 0.0 and end at 1.0, like the middle image. So let's start the evaluation setup. To evaluate our model, we first reconstruct and clean the original dataset. The dataset is collected my previous research of the dual mouse featural test. So it's collected to 23%. So for evaluation, we use the original fit law task condition from the dataset, the movement distance and target width, a total of 12 evaluation conditions. For each condition, we generated trajectories using temperatures generated. So it's generated 20 samples for each condition temperature pair. Finally, the generated trajectories were compared against real human trajectories using geometrics and dynamics movement metrics. To evaluate how closely the generated trajectories resemble real human movement, we use both geometrics and dynamics metrics. The geometric metrics include fetch length ratio and the maximum deviation. We also evaluate dynamic characteristics using peak velocity, mean acceleration, and mean jerk. For all metrics, we compute the ratio between generated trajectories and real ones. So first, we start the baseline. So we first train the standard CAVE and GRU model using position reconstruction laws and KL divergence. The model successfully learned the overall trajectory shape and consistently reached the target position. At first glance, the generated trajectories appeared realistic. However, as you see the trajectory example image, trajectories were excessively smooth and lacked the small correction commonly observed on real human cursor movement. Although the geometric shape was reproduced reasonably well, but the movement dynamics such as acceleration and jerk were significantly lower than those of the real data. The result suggests that reconstructing position alone is not sufficient for generating realistic human-like causal trajectories. The baseline model successfully reproduced the trajectory shape, but it failed to capture realistic movement dynamics. So we increased the sequence length and introduced explicit velocity and acceleration reconstruction losses. We expected those modifications to improve temporal resolution and recover human-like motion characteristics. However, the results were not as expected. Although the generated trajectories still followed reasonable fetch, the results that directly matching velocity and acceleration at each timestamp tend to average our natural human variability, resulting in overly smooth trajectories. As a result, we conclude that pointwise dynamic reconstruction alone is insufficient for modeling realistic human causal movement. So this is the second version of our deep learning model. That is the result. It looks like well, but I think the shape is too much smooth. Not the baseline, but it's also too much smooth. So the dynamics loss model shows that directly reconstructing velocity and acceleration was not sufficient. So we hypothesis that human movement should be modeled as a distribution rather than the fixed sequence. Therefore, we introduced statistic-based losses instead matching timestamp. We added acceleration statistic loss, jerk statistic loss, and deviation statistic loss. These losses encourage the generated trajectories to match the overall statistical characteristic of real cube. The result improves substantially, acceleration increases, and while jerk also improve, the overall movement dynamics become much closer to real human trajectories, as you can see the quantitative comparison. The results suggest that distribution level matching is more effective than pointwise dynamics reconstruction for modeling realistic causal movements. So this is the third version of our model, but it also not that much perfect. So although the model is successful, but we observed that the generative trajectories still lacked sufficient corrections near the target. Therefore, introduce fetch length statistic loss together with the late acceleration and the late jerk losses. These losses specifically focus on the final phase of movement where humans often perform fine corrective action before reaching the target. The model shows improvement in acceleration, jerk, and trajectory deviation. One limitation was peak velocity increases, and some trajectories developed sharp correction near the endpoint. Therefore, stronger late dynamics alone did not lead to the best overall behavior. So the peak velocity is too much increases compared with the before version. So like I said before, peak velocity is too much increases, so the result is looks like just a one trajectory spread. So it's not work well. So after observing the side effect, we reduce the weight of the late acceleration and the late jerk losses to less than 1/3 of their preserved previous values. In addition, we introduced the peak velocity statistic loss to explicitly control unrealistic speed spikes. The goal was to preserve human-like correction, therefore, resulting model achieved the best overall performance among all tested configurations. Overall result is improving. Also, the final average metric error decreased to 0.156, which was the best result obtained in this study. So these results indicate that the balanced combination of trajectory geometry and movement dynamics is essential for generating realistic human-like causal trajectories. So this is our final model. So I guess the fetch looks like more twist. So it's very similar compared with the other model. So this is our trajectory evaluation. So this is our heat map, shows how closely generated trajectories match real trajectories across original AW task condition and sampled sampling temperatures. Lower gap indicate better similarities to real mouse behavior. So our temperatures is looks like 0.5 is best condition. The final model successfully reproduced the overall geometry of human causal trajectories. The result was reached similar of the real value. The peak velocity was also well controlled and remained closed. These results indicate that the model captures the overall movement shape and the speed profile effectively. However, these limitations still remain. For the acceleration and jerk, this suggests that certain fine-grained motor correction are still missing from the generated trajectories. Overall, the model reproduced human-like trajectory structure and movement behavior reasonably well, but further improvements are needed to fully capture subtle movement dynamics. So, like as we saw twice, but this is the our current fast model. So this work provides several important implications. First, human causal movement should be viewed as a distribution rather than a single deterministic trajectories. Even under in identical task condition, multiple human-like movement can exist. Second, trajectory shape alone is not sufficient for realistic movement generation. Human-like behavior also depend on velocity, acceleration, jerk, and target approach dynamics. Third, our results show that distribution level loss functions are more effective than the pointwise dynamics reconstruction for preserving realistic movement characteristics. Finally, this approach may help reduce the cost of collecting large-scale user data by enabling the generation of realistic synthetic causal trajectories. So the results can be applied in the three main directions, but this is just just a page of using advanced deep learning classes, so it's not necessary. So application is good. So the overall, this model can reduce data collection costs and support scalable ACI evaluation. So, conclusion, we propose the CAVE GRU framework for generating human-like cursor trajectories under Fitzgerald conditions. So distribution level statistic laws significantly improve acceleration, jerk, and overall movement realism. The final model achieved realistic trajectories geometry while preserving important movement dynamics. These results suggest that human movement should be modeled as a distribution rather than a single deterministic trajectories. So we believe this approach can support future ACI research, user simulation, and synthetic interaction data generation. Thank you for listening. So if you have some question, please Discord to me or DM to me. Thank you.